Hi, so I want to talk about the maximum independent set problem, which is something that we've done on the channel already, where we talked about solving the maximum independent set problem on trees in linear time, but I want to handle the general case now. So what is this problem? So suppose that we got a graph right here, the graph is in red, and what the maximum independent set problem is picking some vertices. I picked these blue ones right here, and I want to pick the maximum number of vertices possible so that there's no direct connection between any of the vertices. So here I pick 3. There's no direct connection between these two, no direct connection here. There's a hop in the middle right here, but it's not a direct connection. And so this is an independent set. It may or may not be the maximum size one, but it is an independent set nonetheless. There's no direct connection between the vertices. So suppose that I wanted to add, let's say, that vertex in, then there's a direct connection between these, and so it's not an independent set anymore. If I tried to add that vertex, then there's obviously a connection. This one has 2 direct connections, which is even worse. And so does this one, which is not good. So what we have right here, these 3 is a maximal independent set, which means that I can't add any more without making it not an independent set anymore. But it might not be the maximum independent set, because there might be some totally different configuration in here for which you can get 4 or more vertices that are an independent set. But here I think 3 is the maximum, but I have not checked. So what we want to do is we want to solve the maximum independent set problem as quickly as possible. And this is a famous NP-complete problem. So it's not known whether there's a polynomial time algorithm for it or not, but we want to do as best as we can nonetheless. All right, so what can we do? Well, what we can do is we don't know necessarily what the size of the independent set that's maximum is. So what we can do is just try all possible subsets, right? Because one of the subsets of the vertices is the maximum independent set size, at least one, there may be many. So the brute force idea is just try all possibilities. So the brute force idea is to try all possible subsets. So this is something that I always recommend that you do. If you have a problem that you don't know how to solve, just do a brute force solution first to get something on the table. Maybe it is the best one. In this case, it won't be, but try all possible subsets of the vertices. And if there are n vertices in this thing, then the number of possible subsets is 2 to the n. And what is the time to check each one of them? Well, I would have to maybe go through every pair of vertices in the subset and then try and see if there's an edge there. You can actually do it in linear time, I think, to see if there's any direct edge connection between. But nonetheless, it's going to be big O star. The running time is going to be big O star of 2 to the n. So the star here is going to suppress all the lower order terms that are multiplied by here. So the actual correct answer is going to be 2 to the n times n if you use just normal big O, but here we're using big O star, so we can forget the little n because it's just so minuscule compared to 2 to the n, it's just not worth thinking about. The runtime here is dominated by 2 to the n here. Okay, so that's just trying all possibilities. But could we do better than this? And certainly we can. And we can kind of get an idea just by looking at this. So let's look at this example a little better. So I want to pay attention to that vertex. So this vertex is what we call a degree 1 vertex, or we could even potentially have some vertex out here that's just not connected to anything. If we have a vertex that's just not connected to anything, then there's no reason why we can't just select it because it's just not connected to anything. It can't hurt us to include it. In fact, it'll help us, which is good. But let's look at this degree 1 vertex right here. Remember, degree is the number of edges that it's attached to. So let's look at this one. So it's either the case for every single edge that we either pick no of the endpoints or we pick one of the endpoints. It's impossible, of course, to pick both endpoints of a single edge because we're trying to find an independent set here. But it might be possible that we have neither of the edges selected. Neither of the endpoints selected, because we're not required to have every edge be covered or something. So it's either 0 or 1. Well, if we have neither of these vertices picked, then that's just a waste, right? Because if this one's not picked and this one's not picked, we might as well just pick this one because it's not connected anywhere else. So we must pick one of these two vertices. Well, let's suppose that we pick this one. Oops. Let's suppose we pick that one. Well, here, we might as well assume that let's try to get rid of this vertex right then. So if we got rid of that vertex, now what happens is that this vertex is isolated. And so in the independent set, we might as well pick this one in the modified graph. So if we bring it back, it's not that hard to see that it could be that the maximum independent set size can be done with this vertex, but it also can be done with this one. So without loss of generality, if there's a maximum independent set, there is a maximum independent set with this one picked. There might be a totally different one with this one picked. That totally might be possible. But there is a maximum independent set with this one picked. So we might as well assume that if we have a degree 0 or a degree 1 vertex, we always will select it, always, which is kind of cool. So let's write down a faster algorithm. So let's do maximum independent set of a graph G. So we need to have some base cases because this is going to be a recursive algorithm, as most of these fast algorithms are going to be. So if it doesn't have any vertices at all, then we might as well return 0 because if there are no vertices, there's nothing I can pick. So if G is empty, we'll return 0. If G has a degree 0 or 1 vertex, let's call it V. Actually, I'm going to put it over here. Then what we're going to do is we're going to return, well, whatever the maximum independent set size is other than this edge right here, essentially. So let's look at this a little better. So suppose that we pick this one now. Well, we can't pick this vertex anymore. So I'm going to get rid of that vertex and every edge adjacent to it, of course. And then now, whatever the maximum independent size of the remaining graph, I'm going to compute that number and then add 1 for whatever was picked here. Okay, so this is going to contribute 1 to the maximum independent set size, and this is going to contribute something, whatever it is. And so I'm going to recurse that way. So what I'm going to do here is I'm going to return 1 plus calling the maximum independent set, not 1 again, maximum independent set size of the original graph without the neighbors of that vertex. So without the neighbors of that vertex. Okay, so we might as well assume that this neighborhood of vertex V is going to include the vertex V itself, because we're not going to be able to pick a vertex twice, obviously, because that's not what an independent set is. Okay, so we're going to get rid of the vertex as well as everything that it's connected to. Here, if it's degree 0, it's not connected to anything. If it's degree 1, is only connected to one thing, so we're only going to get rid of either 1 or 2 vertices here, either the vertex V or the vertex V plus the one that it's connected to, which is pretty nice. Okay, and this is actually pretty efficient. If we're consistently in this case, then we are good, because we're removing 1 vertex from here, And so if we're perpetually in this case, then we're going to subtract 1 from the number of vertices, and we only have a small amount of overhead in doing so, which is just removing 1 vertex at most every single time. 1 additional vertex, I should say. And adding 1 is obviously not that much. So what are the hard cases is when we have a vertex that's connected to a lot of things. So let's think about how we would actually do that. So if we have a vertex that is, the case that I want to think about is when it has 3 or more things that it's connected to. So if it has 3 or more, then what are we going to do? So let's think about what this vertex has. So I'm going to scroll down here. So let's say that we have some vertex V right here, and it's connected to a whole bunch of stuff. Then what are we going to do? So if we think about, let's say that we wanted to pick this thing. So let's pick this vertex. Then what are we going to do here? Then what we're going to do is think about what are the possibilities. What are the possibilities here? It's either that we include this vertex or we don't. It's really that simple. We either include it or we don't. So how do we solve this case then? It's we recurse on one case being that we pick this vertex and we delete all of its neighbors because they can't also be picked. And we also recurse on when this vertex is not picked. So we delete this singular vertex and recurse on the resulting graph. So let's think about how we would do that then. So if G has a vertex V, I'm still going to call it V, of degree at least 3. The 3 is actually important here, and we'll see why. So then what we're going to do is just the normal recurse on either including it or not. So I'm going to have 2 possibilities. We either include V or we don't, and I'll take the maximum of the 2 because we want the maximum size. So I'm going to have V included to be 1, which is we're including it, and plus the maximum independent set size of G without the neighborhood of that vertex. Okay, because that's what we need to do. And then what else can we do? Well, let's have V excluded to be, well, we're not including any vertex here. We're eliminating just that one vertex V, and that's going to be just calling maximum independent set size of G without just V itself. So I'm not deleting any of its neighbors because they may or may not be included. In fact, we would want to include some of them. But here we're not including this one vertex V. Here we are including V, so we need to delete all of its neighbors also. And so what I'm going to return here is the maximum of the 2. Return the max of V included and then V excluded. All right. So why is the 3 important? So suppose that we are not in any of these 3 cases. It's not empty, there's no degree 0 or 1 vertex, and then there's no vertex of degree at least 3. Then that means there's a degree, every single vertex is of degree 2. Okay? Every vertex in the graph is of degree 2. Why is that important? So let's think about what degree 2 vertices mean. Well, if we have a bunch of vertices that are of degree 2, then they must form a collection of cycles. So if we have every vertex of degree 2, I can't stop prematurely because then there's a vertex of degree 1 here, and we assume that there isn't one. So it must eventually form a cycle, but we can have multiple of these cycles, of course. So maybe we have a degree 4 cycle, maybe we have a degree 3 cycle, and the graph is just a collection, a union of cycles. And so what is the maximum independent set size of all of these? It's the number of vertices in each divided by 2 and then take the floor. So let's actually look at this here. Well, the degree 3 one, the 3 vertex one, I can only pick one of the 3 vertices. I can't pick 2 because they're all connected to each other. The 4 vertex one, I can pick the opposite ends one, or the other way around, but I can only pick 2. So what is this one? This one is 1, 2, 3, 4, 5, 6, 7. So predictably, I should only be able to pick 3. So here I can pick that one, then that one, then that one, and I can't pick any of these 2 because they're connected to an already picked one. And I can't do better than that, because if I leave, say, like that one out, then this edge has, this edge will be completely left out, but then I would have fewer things picked over here. So if I left this guy out, then I will only have 2, which is obviously smaller. But the only way to pack them in better is if I pick every other vertex along the way and then potentially miss 1. And so that's where the floor comes in. The number of vertices in each cycle divided by 2 and then take the floor. And that's all that you have to do, which is pretty nice. So, and then otherwise, so all of these are really else's. Because they're all mutually exclusive at this point. But in fact, you don't really need the else's here, because in order to, in each one of these, we're returning immediately. We're not relying on anything else. So these else's are kind of not necessary, but it's just nice to read it that way. So then else, G, in this case, G is a union of cycles. If I could spell cycles, that'd be good. So then all that we have to do in this case is return the sum of the size of the cycle for each, in this case, they're connected components of G, and I need to return the size of that connected component divided by 2 and take the floor of that. I know it's a little messy, but it's the size of the component, which is the cycle itself, divided by 2 and then take the floor. Okay, and then so this is pretty efficient because finding connected components can be done in linear time or polynomial. It doesn't actually matter the exact amount of runtime. It's just polynomial here. This one is essentially just t of n, the time for n vertices, is essentially the same as t of n minus 1. So the big workhorse is this one. So the real runtime of this thing is dominated by repeatedly choosing this guy right here. And if you analyze it, though, if you're in this case, what is the actual runtime? Well, the time on n vertices is going to be, well, this one right here is obviously n minus 1 vertices because I'm deleting 1 right here. So that's, and there's only one of those calls, so t of n minus 1. And then here, this one, the neighborhood of this vertex v is at least 3, and we're deleting the vertex v itself, which is cool. So we're actually deleting 4 vertices at least here. In fact, we could be deleting a lot more if v has a very high degree, but here it is, we can only guarantee it's at least 3. You can actually get a better runtime by analyzing if it has like degree 4, degree 5, and etc. vertices after that, just by looking into the graph a little bit more. But here, let's just assume we do the absolute worst thing, which is only 4 vertices deleted here. So this case is t of n minus 4. And then the time to combine these solutions, well, to find the neighborhood is linear time. The time to delete a vertex is linear time, let's just say, or just some polynomial to make it easy. So let's just say plus n to the c for some number c. And if you work through the characteristic polynomial of what this represents, which is effectively saying solving the equation r of, actually I'll do it this way, so it would be x to the 5th is equal to x to the 4th plus x. I think that's right. Actually, no, I'm not 100% right. So if you solve the equation x to the 4th is equal to x to the 3rd plus 1, then the solution for x will be the base of the exponent. And if you do that, say with Wolfram alpha, then t of n, based off of this, is going to be big O star of x to the n. And if you actually solve what that number is, it will be 1.38 to the n, which is significantly better than the 2 to the n example that we had, which is the brute force. So just by simply analyzing the graph that we have and being able to have an example where we have a bunch of cycles, which is a really easy example to solve because we have maximum independence set, makes this a lot better because we were able to increase this threshold higher than 2. If you can increase this more, then you'll decrease the running time in total because this number is going to be decreased even more. All right, so this is a fast, or at least faster, algorithm for the maximum independent set problem that we were able to solve in 1.38 to the n time. There are faster algorithms than this, but they're considerably more complicated. This is a really nice example of being able to have simple cases that have a much faster runtime than a brute force solution.